take some notes out and get ready here, so I'm actually ready to start now. All right, so August 24th. We're going to be reviewing section P-3, and this is going to be a review of radicals. Okay, so in Algebra 2, you did everything. You did an entire chapter on radicals. You did adding and subtracting radicals. You simplified radicals. You probably multiplied them. All right, so this is just one section. So again, just like things that you did in Algebra 2 and it took you a long, long time to do, like an entire chapter, we're going to do it all in one section today. All right, so to begin with, they are going to start you out with the very basics, like can you do something like negative square root 25? All right, they just want you to be able to do simple square roots and then know how to handle a negative in front of that. So that one's pretty simple. We know that one's going to be negative 5. All right, now in this section at the beginning, they are going to assume that you do not yet know about imaginary numbers. So like square root of negative 36, I mean, you do know how to do that using an I with imaginary numbers because you went all the way through Algebra 2. But in this section, since we're right at the beginning of the textbook, they're going to assume you don't know imaginary numbers, so they want you to answer this as it's not a real number. All right, it has an answer, has an imaginary answer, but they don't want you to give it a 6i. They just want you to say it's not a real number at this point. Then they may actually do some problems where you've got more than one thing underneath the radical. So like 25 minus 16. All right, if there's some type of operation under there, you are to do, it's almost like a set of parentheses. You've got to do what's underneath there first and then take square root. So if I would subtract that, I'd get what, 9? So square root of 9 and then square root of 9 is 3. All right, now comparing that to a problem that looks like the square root of 25 minus the square root of 16. All right, these two problems should look different to you. All right, they are worked different. I got a single number under here, which means I can take the square root right away. So I can do a 5 there. I can do a 4 here. 5 minus 4 is going to give me a 1. See, so these two problems do not end up with the same answer. Okay, so again, very, very simple here. Now, they do want you to be able to do variables. You did variables under in Algebra 2. Right here in this beginning section, they're not going to worry about absolute value bars, okay, which I don't know if you did any in Algebra 2. You should have. When you simplified your radicals with variables, you should have used some absolute value bars. But what we're going to do is we're going to assume all variables are positive. All right, so let's actually write that. Assume all variables are positive. And then what that allows us to do is it allows us to avoid those absolute value bars. Okay, so like let's do square root of x to the 4th. We're going to do really simple ones. All right, if it's an even exponent, it's going to be a perfect square root, right? Because I can find something when multiplied by itself equals the x to the 4th. So what, x to the, we know what it is? What times itself will give you an x to the 4th? X squared, okay? So this is an x squared because x squared times x squared equals x to the 4th. When multiplying like bases, you add the exponents, okay? So that's why. All right, if it's an even exponent like that, it's always going to work like that. Okay, so another even exponent then, square root of, say, x to the 8th. X to the 8th is going to be x to the 4th. Okay, so basically when it's an even exponent, you can do half of it because that times itself will be that on square roots. All right, now when it's an odd exponent, let's do like square root of x to the 7th. Okay, so obviously I can't add the same thing. Like over here I added x squared plus x squared. I got the x to the 4th. I can't do that because this is an odd exponent. Okay, so now you're going to use the little factor tree type thing and you're going to break this up. You want to break x to the 6th up into the highest even exponent. So I can't break up a 7 there, but if I do x to the 6th, I could do, that would make it an even exponent, and then it's a perfect square root. So I'm going to break this up into the square root of x to the 6th. All right, now what has to be multiplied by that to get that x to the 7th? That would be an x to the first power. When multiplying like bases, add the exponents. That 6 plus 1 is going to give you the 7. I want to do this because this is a perfect square root. I'm going to abbreviate there. All right. So always one number less than that odd exponent will give you an even exponent, and that's always going to be a perfect square root. So then from here, this we know is x to the 3rd, and then that is just going to stay square root of x. You can break up every odd exponent variable like this every time. Okay, so let's do it again. So if I had square root of x to the, I don't know, say 13th. All right, you want to break it up into an even exponent and an odd exponent. You want the biggest even exponent because you want the biggest perfect square. So that would be, break this up into a square root of x to the 12th, and then x to the 1st, because 12 plus 1 equals 13. This one is a perfect square root because it's an even exponent, so this is going to become x to the 6th, and then square root of x. Okay, so at the very beginning of section P-3, they're going to be this simple. They're not going to be harder than that. Okay? All right, good so far? Okay. All right, they will then put the concepts together, and they'll do a variety of things. Okay, so the directions are probably going to say simplify. All right, let's suppose you had the square root of 45 x to the 8th. All right, now when I have something like this, I take care of that coefficient, and I simplify that radical, and then I take the variable and I separate that, and I do them individually. Okay, so really I would look at this as a square root of 45, and I would work to simplify that the way you did in Algebra 2. All right, this one is square root of x to the 8th. Okay, now we did the little factor trees on this, right? Again, if you pick the biggest perfect square root that goes into 45, your tree over here is going to be very, very, very small. Okay, so you're looking for, you know, numbers that are squared. So I would try to put 4. Does 4 go into 45? It does not. That's 2 times 2. 3 times 3 is 9. Does 9 go into 45? Yes. All right, the next one would be 4 times 4 would be 16. Does 16 go into this? Nope. 25 doesn't go into it. 36 doesn't go into it. All right, so that means that square root of 9 is going to be the biggest. The biggest perfect square root that I can. 9 times, what, 5 is 45? All right, by doing the biggest perfect square root right here, you are ensured a very, very small tree. So this part simplifies to a 3 square root of 5. All right, now focus over here. It's an even exponent. All even exponents are perfect square roots. So I can just immediately take square root there. So x to the 4th. Because when you take the square root, this radical bar goes away. All right, so this is on the outside, this is on the outside. All right, anything on the outside of the radical gets put in front. The 5's the only thing underneath the radical now, so 3x to the 4th square root of 5. 3x to the 4th square root of 5. Okay, when you are breaking this up, all right, things are being multiplied together, okay? When you write your final answer, those dots are going to go away because you're going to write it nice. Okay, you also are going to see some quotients. All right, so to begin with, they may do a big radical and a couple perfect square roots underneath there. There is something that says when simplifying radicals, if I've got a great big radical and it's going to benefit me, I can break it up into 2 little ones. So technically the next line of work is square root of 49 over square root of 16. And that works on this one because they're both perfect square roots. So 7/4. All right, no reason turned into a mixed number or anything like that. Just leave it 7/4. From here to here, this is a property of radicals that says I can legally do that. I've got one great big radical. I can break it up into 2 little ones. All right, this rule works both ways. All right, so if I had it already in 2 individual radicals, like square root of 48x to the 3rd over square root of 3x, All right, 48 is not a perfect square root. 3 is not a perfect square root. So I'm going to use this rule in reverse. I've got two individual ones, so then the rule says I can write it as one great big radical of 48 x to the third over 3x. That allows me then to work with whatever's underneath that radical and simplify it. Okay, can I take 48 divided by 3? I can, right? 48 divided by 3, 16. All right, now laws of exponents that we reviewed last week, x to the third over x, there's that little imaginary 1, is what, x to the second. So if I simplify this, I get a 16x squared.
At this time, can we have freshmen E through K? E through K in the main gym for pictures.
Okay, so picture day, we're going to have announcements all day long. Okay, so both of these now are perfect square roots, so we're going to have a 4x. Okay. So far, so good? Okay, can we probably do enough of those? Is that enough of those simplifying? Okay. All right, let's go on to adding and subtracting. Okay, because you have to simplify, you have to add or subtract, and I think you're even going to have to do some multiply on this. All right, so adding and subtracting radicals. Adding and subtracting radicals. Okay, so whenever you add or subtract, it's almost like adding and subtracting like terms. You have to have like radicals. Okay, so I'm just going to write down like radicals. Obviously, they'll give you one or two. Since this is a review, they'll give you a couple where the radicals are already alike. So they might give you something like 3 square root of 17x minus 7 square root of 17x. Okay, these are like radicals in the sense that they're both 17x. They are both square roots. All right, so then I can just subtract these left to right. 3 take away 7 is going to give me a negative 4. And I can get a negative 4. And then adding or subtracting like radicals, you get a like radical, square root of 17x. All right, so you won't have a lot of those to do. You'll have just a few of those to do. All right, now, if they don't have like radicals, they probably will start you out with just numbers initially, like square root of 8 plus square root of 18. All right, but I could put some variables in here. I could have an x squared here. I could have an x squared here. I could have an x squared and a y squared. I mean, I could put whatever variables under there I want, okay? All right, these are not like radicals because this is an 8 and this is an 18. So break up the first one, break up the second one, and see if you can create some like radicals. All right, so you're going to look for the biggest perfect square root that goes into 8, which is going to be 4, right? So square root of 4 times square root of 2. I haven't taken any radicals at that point, so I still have the square roots over them. And then this simplifies down to just a 2. So I've got a 2, radical 2 on this one. Now, hopefully, this one will simplify down to a square root of 2 so I can actually add them. So that might help you make some decisions about what you're going to choose here. Again, I'm picking relatively low numbers for the examples, all right, just so you get the idea. But whatever that number is, you're going to find the biggest perfect square that goes into it, which is 9, right? 9 times 2 is 18, so this one does simplify down to a square root of 2, so I'm going to have 3 radical 2. All right, now I've got to the place where I have like radicals, so I can add the coefficients there in front, and I can get a 5 radical 2. The numbers in the book will probably be bigger than 18 and 8, all right, obviously. All right, but conceptually here, I'm using small numbers so that you just get the idea of how we do it. All right, the thing is, all right, I verbally said it. I don't know if you're picking up on it. This number right here is the biggest perfect square root that I can find that goes into 8. The biggest perfect square root that will go into 8. If you do that, then every time your tree is just going to have the 2 rows in it. If you find the biggest perfect square root, it will work out really nice. All right, so there's adding and subtracting, okay, just as a quick review. All right, let's look at rationalizing the denominator. Okay, so rationalizing the denominator. You're going to have two main type of problems that they're going to want you to review. All right, two main type of problems that they're going to want you to review. Something that's maybe just got a plain square root on the bottom, okay, and maybe even a whole number on top. So like 3 over square root of 5. All right, they're wanting you to do this just to get you back in the swing of things, remembering how to do this. All right, rationalizing the denominator means that I cannot leave that radical 5 in the bottom. They like for you to do that when you're simplifying your radicals. So if I take this fraction and I multiply by a form of 1, I'm not changing my original problem at all. Okay, so I pick whatever that denominator is, and I turn it into the form of 1, so I go square root of 5 over square root of 5. I'm multiplying by 1, so I'm not changing that original thing at all, but what's going to happen is it's going to get rid of the radical on the bottom, which is what we want to do. If I multiply a number and a radical on the top, I'm just multiplying. So 3 square root of 5. All right, now you can do an extra step in here, or you don't have to do that extra step. All right, when you multiply two radicals, you are allowed to multiply what's underneath, right? So 5 times 5, I'm going to write it right here, is really square root of 25, right? But square root of 25 is 5. All right, so in Algebra 2, they taught you whenever you're multiplying two square roots with the same number underneath, and it's always just that number underneath. But that's why you can multiply 5 times 5, you get square root of 25, and then when you simplify that, you get to 5. Okay, so everybody remember doing that? All right, and then I could, this is an integer on top. All right, I could have a radical on top, so let's go ahead and do one with a radical on top. Let's suppose, and let's stick with 5, square root of 2 over, well, I could do square root of whatever. Let's do, yeah, 5's fine. If that was square root of 6 or square root of 7 or square root of 8, it doesn't matter what that denominator is going to be. You're going to pick the denominator, multiply by a form of 1. So square root of 5 over square root of 5. Now I've got two radicals. All right, the top, I'm going to multiply underneath. That's going to give me square root of 10. And this on the bottom will simplify all the way down to a 5. Now on this one, we are done on this one because that square root of 10 doesn't simplify. But if that would have been square root of 20, then you would have had to done the tree, break it down, and keep going from there, okay? All right, so you will have to rationalize the denominator when you have just a single radical in the bottom. You are also going to have to rationalize when you have a binomial in the bottom. Okay, so maybe let's say you have 13 over, say 3 plus square root of 11. Okay, they're going to put a binomial in that bottom. Now if you remember, there's a certain way we choose to form our 1 here, and you just memorized it probably in Algebra 2 and didn't really realize what it was, but when you had that binomial there, you always chose the opposite sign to multiply. Okay, that's because if I choose a 3 minus square root of 11 over a 3 minus square root of 11, that's number one, it's called the conjugate. All right, but if I multiply this right here, this binomial times this binomial, that's factored form of the difference of two squares. So if I FOILed this out on the bottom, I'm only going to get two terms. I'm going to get the difference of two squares. All right, so I can quickly multiply. I can square the first one. I can square the second one, and since I know it's the factored form of the difference of two squares, I automatically put a minus sign in there. Okay, so that's why we choose to do that. So let's actually write conjugate above that, just so you've got the vocab. All right, you are choosing to multiply by the conjugate there. All right, now you've got to remember that this is treated as a binomial. All right, so I'm going to actually put an extra step in here. So on the top, I've got a 13 times the binomial 3 minus square root of 11. On the bottom, since I know that this is the factored form of the difference of two squares, I can take the first one and square it. I can automatically put the minus sign down because it's the difference of two squares. I can take the second term which is square root of 11, and square it. Okay, so let's write down difference of two squares right there. Difference of two squares. We're choosing to multiply by the conjugate so that it forces a difference of two squares on the bottom, so I can multiply that out really easy. Okay, now let's go ahead and distribute on the top. That's going to give me a 39 minus the 13 square root of 11. Alright, on the bottom, I'm going to have then 3 times 3 is 9. Square root of 11 times square root of 11 is going to be 11, right? Minus 11. Okay, now let's keep going here. On the top, I'm just going to, at the moment, leave it 39 minus 13 square root of 11, and then on the bottom, I'm going to get a negative 2. Alright, now, the textbook does not want you to leave it like this. Alright, the higher up in math you go, like this is pre-calc. And then the next step, if you're going to keep going in the progression, would be calculus. You don't want to leave an answer like this. You don't want to leave a negative in the bottom. You kind of want to clean up answers. Okay, so what the textbook's wanting you to do is get rid of the negative in the bottom. I can do that by multiplying this entire thing times a negative 1. If I multiply it times a negative 1, basically what's it do? It's just going to go through and change all your signs, right? So this 13 square root of 11 becomes positive, the 39 becomes negative, the 2 becomes positive. So I'd have like a negative 39 plus 13 square root of 11 all over 2. Just kind of cleans it up and prevents that negative from ending up in the bottom. Okay, so two different ways to rationalize: when it's a single radical on the bottom or when it's a binomial on the bottom. Okay, we good there? Okay, now they're also going to want you to do higher powers. If you've noticed, everything that I've done so far, they've all been square roots. Okay, square roots, square roots. Everything we've done has been square roots. In Algebra 2, you should have done some cube roots, fourth roots, that sort of thing. Alright, so roots of a higher power. So like say n of x. Nth root of x. And I could put any number in there. I could do cube root, fourth root, fifth root. Alright, I'm going to try not to do too high of numbers for you. But like, and I'm going to pick real little ones here, like cube root of 8. Okay, I did that on purpose so it'd come out even. Alright, so if it's a cube root, you're looking for a number which multiplies by itself 3 times. If you had a fourth root, you're looking for a number which multiplies by itself 4 times. Alright, so can we do cube root of 8? Cube root of 8 is going to be 2. Alright, because if I took 2 times 2 times 2, if I did it 3 times, I get that 8. And so, why am I writing 8? So the answer is 2. Okay? Alright, and then, obviously I picked really low numbers, so this would work. So the fourth root of 16 is, again, 2. I did that on purpose just so it'd be nice and easy, but it's to show the point. 2 times 2 times 2 times 2. Alright, 4 times, so I multiply it by itself 4 times. Alright, then I get that 16. Alright, now, the very last thing they're going to expect you to do. So my assumption is in the homework, since this is just a review section, you're just going to have to do maybe a couple of third roots, fourth roots. The numbers will be relatively small, okay? Now, let's do a definition that's in this section they want you to review. Let's suppose I had an a raised to the m over n. So in other words, some base raised to an exponent. Okay, now there's two different ways that this simplifies. The denominator of that fraction is always the root. Alright, but I can choose to take the root of that base and then raise it to the nth power, or I can choose to take the base, raise it to the nth power, and then take the nth root of it. Alright? Now, either way works, but stop and think about what's going to happen. If I have some base and I raise it to the m power, what's going to happen to that number? It's going to get really big, right? and then I'm going to have to take the nth root of a really big number. So I don't want to do it that way. I mean, can you? Yes, but I would not necessarily want to do it. I want to start with whatever that base is and take the nth root of it. While it's a small number, it gives me another small number, and then raise it to a power. All right, just easier on the numbers. Okay, so
At this time, if we could get sophomores, A through D, sophomores, A through D, in the main gym.
all right, so on this, I've got 27 raised to the 2/3 power. Okay, so like I said, you could set it up either way, but I want to do the third root of 27 first to get a relatively small number. So I'm going to write it as the third root of 27, okay, and then square it. So the third root of 27 is going to be a 3. Yep, so I'm going to have a 3 squared, because 3 times 3 is 9 times 3 is 27, so it is 3. And then I'm going to square it, and then I get 9. All right, had I done it the other way around, 27 squared, I can't even do it in my head, a really big number. All right, and then try and take the cube root of it, it just would have, you would have had to grab a calculator, okay? So that's probably the easiest way to do it. All right, now, last week we did do laws of exponents and some negative laws of exponents, right? So they're going to throw some negatives in because they're combining. As we go through this review chapter, they're just going to put all the concepts together. All right, so like if I had an 81 to the negative 3/4, all right, so we learned last week with laws of exponents that we can't have negative exponents, right? So I would probably get rid of the negative first. I would move this entire thing to the bottom, make the exponent positive. That would leave me with a imaginary 1 on top, right? So I'm going to have 1 over 81 to the 3/4. All right, use that laws of exponents to turn that exponent into a positive number. All right, then apply this rule. And again, I want to take the 4th root of 81 so that I can get a small number and then raise it to the 3rd power. So the 4th root of 81 first, which will get me a relatively small number, and then raise that to that 3rd power. 4th root of 81. You might know what that is. It's not 2. It's got, let's try 3. 3 times 3 is 9 times 3 is 27 times 3 is 81. Yeah, so it's 3. All right, so 1 over 3 to the 3rd. And then we already know 3 to the 3rd is 27, right? 3 times 3 is 9 times 3 is 27. So then I'm going to have 1 over 27. All right, so they will expect you to apply and learn things that we did earlier in the chapter. Okay? Now, like I said, what this P chapter is, you're going through really, really quickly everything that you've done in Algebra 2, just at a really fast pace. What I just did in today's lesson would have been an entire chapter in Algebra 2. Now it's one section because hopefully you've already mastered it, and all you needed was a little bit of review just to remember how to do this stuff. All right, anybody have questions? Are we good? Okay, so you should have again another book assignment. All right, so I'm going to give you the rest of the period to work on it, so you should get a large portion of it done before you leave.